Good evening, everyone. Okay, let's see if this works, and if it works, then we can get the stream going. I guess there was no stream for the last month, right? So we have a lot of stuff to catch up, I guess. Yeah, it seems to be working. That's actually perfect. But first things first, today's moderator is Foxtrot Charlie. His nickname is right here. Yeah, here. So if you have any questions during the live stream, do ask Foxtrot Charlie on our YouTube or our IRC chat. So he can pass the question to me. We do have a telepathic connection, so that actually works. Yeah, so a month, that's quite a long time. I actually hope to get back to regular streaming, but in all honesty, that's not going to be easy. There will be no live stream next week, I apologize for that. And then there will be another break around November since I'm on some conferences. But yeah, I hope December is, and like January and so on, they will be like pretty regular then, hopefully. Oh yeah, and on IRC you can use !Q to actually ask a question as well. So today's topic is going to be Dragon CTF, or actually Teaser Dragon CTF 2018, which is the CTF created by Dragon Sector, which is a CTF team which I am a member of, and actually a creator of as well, but not the captain anymore. That would be Valis. So yeah, the CTF was run last weekend, as in a few days ago. It was 24 hours only, teaser format, teaser Jeopardy format. That means there were only a couple of challenges, just to, you know, show the folks what to expect on the main CTF. And the main CTF is going to take place in November in Poland on a Security Pwning conference, which I co-organize. It's going to be a full format ranked Jeopardy style CTF. It's open for conference participants, so you do have to actually have a conference ticket to participate. And the teaser was also one way to get the ticket, because several top teams did receive or are going to actually receive a ticket for the conference, so they can participate in the CTF without any additional costs, so apart from, you know, the transportation, hotels and so on. So, well, partly without any additional costs, I guess. So today I will be chatting actually about two tasks from the CTF, tasks which I'm familiar with and which I have created. That would be Brutal Old School, which was Reverse Engineering Easy, or Reverse Engineering 100 as I intended it. So it was solved, I think, around 70 times on the CTF. It was solved already after, I think, 19 minutes or something like that from the CTF start. So that's, yeah, that was intended. I'm going to show it to you how to solve it, and it's super easy. Apart from that, I'm going to show the second task, which was Chains of Trust. Chains of Trust was Reverse Engineering 500, and that was not a trivial task, only 10 solves. I expected kind of that number, give or take 5, I guess. So yeah, that will be the second task I will be describing today. And then if we will have some time, we might also chat about the layout of the website. I'm going to show the layout in a second, because while I didn't create the art for the layout, I did create the design for the layout, then hired a graphic artist to make the art, and then put together with all the, you know, CSS, HTML, and so on stuff. We already had the backend ready, so I only tweaked the front end. But I'm actually quite happy with the layout, so we might spend a minute or two talking through how it was created too. Okay, so let's move on to this. Yes, as you can see, I don't have my normal DNA rotating wallpaper. That's because for some reason it doesn't show up in my wallpaper engine. I don't know why. Actually, I had like some hardware changes as well, so I'm streaming from a new LCD, which is 144 Hz TN LCD screen, which means it's really good for gaming and is really terrible for colors. And yeah, and I'm going to try it today and for the week probably, but I already feel I'm going to fall back to one of my IPS monitors in the end, because the color difference is just like huge from what I see on all the other monitors and my main one. Anyway, so that also meant I had to reconfigure OBS, and yeah, and so that's why I hope I'm showing actually the right desktop, and indeed I am. So as I mentioned, today's moderator is Foxtrot Charlie. You can go to his website. I'm not sure if he posted anything. Let's see. He posted 25th of July. Hey Foxtrot, what's up with that? Come on, dude, just post more stuff. But he does post both in English and in Polish if you're curious about what he does, apart from being the moderator on today's chat. I did mention already the Pwning conference. Most of the lectures are going to be in Polish, actually, but there will be a simultaneous translator. So if you're interested and you're nearby, then get a ticket and come and join us. I think the agenda is already there, though there were some last-minute changes. Oh, it's not in the English version. Oh, there is part of the agenda. That's cool. Anyway, I'm not going to talk too much about it. I'm going to spend a minute talking about the Genville's Summer Game Dev Challenge 2018 because it finished and the results have been already published. So yeah, the first place goes to Shatter Asylum by Mateusz. It's I'm going to show it to you because the games are all playable. Actually, if you go to my blog and then you click, you can play all of them. You get to the list of the games and they are all in JavaScript. Well, that's not true. They are all in web technologies because some are in WASM, which is WebAssembly. Like for example, what was it? Rust compiled to WebAssembly, which was pretty amazing and pretty surprising. I know I listed it actually as the possible technologies, but I didn't expect anyone to actually use it. So yeah, this is basically the game. What I like about it is the lighting system and the graphics. There was a limitation to 32 colors only, and the author went for, as you can see, grayscale. But actually, yeah, you can turn off light and so on. So there is a fully dynamic lighting system and a fog of war system as well. You have a flashlight, and you have folks which you need to fight. And as you can see, they went for the aesthetics of blood being actually red in the opposition of everything else being grayscale, so that adds a really nice aesthetic to it. And yeah, there's also a gun and so on, and everything is 32 colors. The resolution is low because that was the requirement. And it actually has 9 levels. It's a pretty cool game, pretty good overall atmosphere of an asylum, so I really liked it. So that was the first place. Now the second place was Pyra Mami by Vasil Dador. Vasil Dador actually won my previous competition, and this game looks way easier when it comes to, there is no dynamic lighting and so on. The aesthetics are much simpler. That being said, this game is really well done, and apart from that, it allows you to do. It has some really cool physics implemented and logic implemented behind it. It's basically like speedrunning material, as I did write in my blog post. So yeah, do check it out. Actually, do play it, do complete it, and then try to beat your time. It's super fun. Tropical Frenzy by these 3 people, René, Chief, and Daniel, was the 3rd place. It's a well done, complete shooter with quite a lot of levels, boss fights, and multiple weapons. It's fun to play. I came back to this game on and on again, so it's really well done. Congratulations for the 3rd place as well. By the way, there were rewards, right? So, for example, for the 3rd place, it was a gift card of 100 USD. Then there were 3 honorary awards. There were multiple, I don't know how many, 22 games were submitted, and the level was just amazing. I mean, even the simplest game had something fun in it. So in the end, I decided to give out 3 additional honorary awards of 50 USD each. First one went to Mateusz, again Mateusz, though this is a different Mateusz, for the game Captain Coldbeard. It's actually a simple shooter where you're a boat and you shoot other boats, and it's fun to play. It's really fun to play, and it has a shop where you can buy other upgrades and weapons and health and speed for your boats and so on. It's also a pretty complete game. game, so it's fun to play. Then there were 2 3D games. Actually, there were a couple of 3D games, but these 2 use the same aesthetics, as in using this distortion-like effect to emulate more colors, emulate shades of colors, actually. One was called Power Core by yet another Mateusz Timus, and the other was called Grave by Antonio, and Grave Struggle by Antonio. And in terms of graphics, they were pretty similar, with one distinction. The Grave Struggle actually had lightning, as in shadows, dynamic lighting, with the sun moving, so you could see the shadows becoming longer and so on. So that was really fun. The games were pretty close to each other, as in terms of the features. So I kind of treated it like a double honorary award, though each of them get their own, obviously. Very fun to play. They weren't fully complete games, or, well, this was, Power Core was, but it was pretty simplistic in comparison to, for example, well, these 2. Therefore, that's probably one of the reasons it didn't win, but I really did like these games as well. There are quite a lot of other games, and you can play all of them here on this website. So yeah, have fun. They all work under Chrome, because that was the requirement. If you have another browser, then they might work, but in the end, fall back to Chrome if they don't. So that's that. And now we can move on to the Dragon CTF with the artwork. Anyway, so this is how the website looked like if you haven't seen it. No, I'm pretty sure that password doesn't really work, so let's just go with another one. I'm going to create a stream. Yeah, as you can see, I'm just creating a website, so I have to, what do I? Oh, I have to know Polish to be able to pass this captcha. Okay, hills and mountains, at least these 3. Perfect, passwords are different. Come on. Points for you if you can guess my password. It's a really simple password. Okay. So let's sign in. Okay, so yeah, we had a map of challenges, and these are the challenges I'm going to talk about. The sinking boat called Chain of Trust, and this, well, weird-looking tower castle thingy called Brutal Oldskull. So let's start with this one. Yeah, Foxtrot, you're pretty close. Not exactly, but you're pretty close. Okay, so I downloaded the executable, and oh, by the way, before I start, if you go to this blog post on my blog, you can download the challenges, including the source code. So both of them, if you want to see how Chains of Trust was made, download the source code and take a look. Apart from that, there are 2 write-ups for the second challenge, and quite a lot of write-ups actually for Brutal Oldskull. And now this one by Daniel Lee is actually amazing. I've read it today while on a train. It's quite long, very detailed. It's really well written. If what I explained today during the live stream isn't like fully understandable for you, do read Daniel's write-up, because it's just amazing. I mean, Daniel did a really great job, so totally props for that. And yeah, I had a lot of fun reading. I think he got almost everything reversed and right to the details, apart from like one detail or something like that. For example, though I'm going to double check it later on, but I think he claims that the returned byte, which is calculated somewhere, is not used for anything, and I'm pretty sure it was used for something, or at least it was meant to be used for something. So I need to double check if that wasn't a bug in my challenge. But even if it was, it doesn't matter. It wasn't a a hard production, but we'll get to that. So, okay, yeah, brutal old school. Easy, so 68 solves, so let's start with that one. I've downloaded it already, though I do need to create a directory for that. It's a Windows 32-bit CrzaQ, by the way. It doesn't have fancy graphics. It was made like literally a few hours before the CTF, because we are still missing one challenge. So that's why it doesn't have fancy graphics. Otherwise, it would have. I like making somewhat fancy graphics to the challenges, as you know. Okay, APS. 63rd episode of the live stream. That's actually quite cool. So, let me open a console. Here we go. And yeah, this is it. Oldskull.exe, it's 44 kilobytes. And if we look at it, it doesn't have, this is by the way listed from Total Commander. It's a plugin for Total Commander that shows you DLL PE headers, including DLL imports and exports. So these are just the standard libraries. We should expect the C library to be used and the Windows API, but that's about it, which is what we should expect based on the static part of it. We don't know if there's any dynamic part, by the way. And as I said, it's a 32-bit x86 Windows CrzaQ. So yeah, let's run it. And it appeared here. Here we go. This is how it looks like. We need to enter we need to enter these 4 codes and then the flag. And after that we click check, I guess, and something happens. So let's enter something here and click check, and it says incorrect code 3. So this code is incorrect because it's supposed to be 16-bit hex format. But hey, what's up with this? I mean, actually these codes we didn't give them hex format anyway. But what we can expect is actually, it's kind of greedy parsing in a sense that it parses up to wherever is valid. So for example, A is a valid digit in hexadecimal numbers, obviously. And then when it gets another letter which isn't really a hexa digit, which S isn't, obviously, then it just bases out. And well, here actually we started with S, so it's probably, well, it's set, it's in valid format. But so we know it's supposed to be like a hex format, 16 bits, that's what the sign says. So let's do it, and it says the code 1 is wrong. So I guess we already know that we can do it linearly. We do not have to get all the codes at the same time. We can first get the correct code 1, then we can get the correct code 2, and so on, because the error message tells us, like, yeah, this is, you have incorrect code 1. So we brute force, for example, brute force. Well, I guess the brutal in the name is a pretty big giveaway, but we're supposed to do some brute forcing here. Yeah, so we brute force code 1, and when it says wrong code 2, that means we actually got code 1 correct, and we can carry on with brute forcing the code 2, and so on, code 3 and code 4. And then we have to figure out what is the relation between these codes and the flag. Perhaps this is a serial number, maybe it's something else, maybe these are just passwords. I don't know, so we have to figure that out. And if we click about, then, yeah, no, it's like nothing here, but we can say yes, no, or cancel. Let's say no. It doesn't matter what we click, by the way. So, okay, let's run it in IDA. Let's open it in IDA. Okay. Here we go. So I'm going to, I'm not going to read assembly code because, you know, the stream is pretty limited. So I'm going to click tab to switch to C, decompiled C code, and let's go here. This is basically, if you've ever created a window using Window API, then you know this is a standard window creation. You first register a class, you fill out a structure with something, and then you call create window API based on the class name you registered. So this is the class name. And as you can see, it's in, well, it even says it's a class name, right? So this creates a window, which is fine, and there's nothing else here. It's actually like, if the window was created, then show the window, and then get into this loop. This loop exits when the process gets, or the window actually gets a message, quit. And then, yeah, like usually the way you do it is when you close the window, it sends an event quit, and then this loop exits. And while it doesn't exit, while it actually operates and iterates, it calls two Windows API functions, which again are super standard. If you ever done any Windows API coding, you know these functions. One translates a message, I don't really know what this does, and the other one dispatches it. By dispatching, it means it actually calls the window procedure responsible for handling messages for the window, because that's how Windows on Windows work actually. You have a window and it has some functions somewhere. So there is a function, and the window gets messages like, for example, mouse is moving on the window. That's a message like mouse move, or like mouse clicked, or a key press happened, or window became active, or window stopped being active. So these are messages, and the messages are handled by the function. And the function, which is responsible for handling the messages for the given window, is actually given in the window class, because you declare the Windows class once, and then you span windows based on that class. So it's like same like a C++ class, but for window, not for code, right? And there is a field called this local pointer function window procedure. This is the function which is responsible for handling messages for the window. So this is actually the most important function probably for us. So maybe that's not the case, but we will get to that. So this is window proc. Let's just go there. And yeah, so basically it's like this. If again you didn't do any Windows API coding, you get the message ID because there are different classes of messages. Again, like for example, it might have been mouse moving, or it might have been window became active, or somebody clicked the close button, right? So you distinguish that by the Windows message code. And for example, message code 2 means somebody closed the window, and in that case, post quit message. Post quit message is the message which is the function which sends the message quit, which I did talk about a few seconds ago. So this is the chaining of the events which I did mention. But if it's a different message, then we go here. This destroys the window. So it's actually, I think it's like this. Like if somebody clicks it's like this. This sends the quit message, and then later this destroys the window, or it's the other way around. Doesn't matter for us, at least. At least I hope so. Now, most messages are actually not handled by this function, because most messages either don't do anything or have a default action, which is like, for example, if you move a window, you expect it to actually move, and that might be a default message. I don't remember if that's actually the case on Windows API, but let's assume it is. So usually for most messages, you call this default window procedure, which you pass all the arguments and it handles the message. So everything else which is in this function is actually the custom messages which were defined by the author of this task, that would be me, but yeah, still the author of the task. For example, if there is this message and something like one of the parameters, one of the arguments of the message is equal to something, then this message box pops up. And this is the about message box, which we saw a second ago. So we can, just like looking at this, we can derive that this is actually handling a button press. So this message, and I guess that would be message 273, would be handle button click. And it checks which button has been clicked. If the about button has been clicked, then like just display this message box. Otherwise, what other buttons do we have there? Well, there's only one more button, and that would be the check button, right? Check the flag. So in that case, the other button is pressed, go into this function. So this function is actually probably going to check the flag, so this is what we are interested in. So check flag. And apart from that, there's message 1, which is being handled here. And message 1 is, if I remember correctly, you can actually like ask IDA to enum, no, not enum. And yes, we're on standard. It's called VM create. Yeah. And VM create means the window has just been created. Do you want to do anything before it's shown? And one way of creating windows on Windows is actually to fill it out during this event and create other windows, because every button, every input box, and every like text and the window is actually a window of its own. It's a child window. So you could just call the create window API again, but you pass different classes, for example the default edit class, or as we can see later, static for displaying text, or button for, well, there being the buttons. And what is returned here is the handle for the window. So we can actually change this to like HWND button, like check button. And we can scroll up and see that this L param is actually checking for the check flag, right? It's actually checking the handle of the window, you know, the descriptor of the window, of the, well, button window. It's not really a window per se, it's a child window, right? Yeah, so yeah, so I guess we need to look at this on this check flag, and yeah, there's 155 lines of code, but what we can see already here, but in some cases it displays wrong code 1, wrong code 2, wrong code 3 or 4. And just by briefly looking around, right, we can see that it calls create process, so we are to expect that it will create a new process at some point. It also creates a temporary file. It will also open that file for writing. So at some point, what we can derive from this is that it will create a file, and then the file name buffer, and then actually create that, well, span that buffer as a new process. So it will call a new application that it will first write to the disk. Now, the question would be, what kind of application is that? And like, what is going on here? For example, what are these numbers? Okay, looking at this hexadecimally, these are actually like ASCII, this is text. So let's do, okay. So if we read it backwards, that would be old, OLD, old school checker exe. Yeah, so that's old school checker exe. It will create a file named oldschoolchecker.exe, and then it will span it as a new process. Where does it get the data from? And that's a question for fwrite. What is this parameter v18 for fwrite? It's actually a result of this function. There's this function which is called several times. And first, it uses some, what is this? Oh, this is some random looking data. Okay, so this is some random looking data, that's fine. Let's just go back. Sorry, I was supposed to look at this. Then it passes another argument, which is decreasing here. This is probably like a buffer pointer and a pointer to the size of a buffer. That's usually like a pair which you would expect. Like it's same for fwrite, which is the buffer and then a weirdly expressed size of the buffer. That actually means 1 time this. But yeah, this is the same similar number, so we should expect this is the size. And then we have something like v12. What is v12? Where did we get v12? So v12 is actually used here, and it's derived from v2. And v2 is scanf. So, and getWindowText. So getWindowText, for when used on the input box, actually gets you the text which was put into the input box. So that means that this gets the whatever you put into an input box, and please note that this is a for, so this is happening 4 times, and we have 4 codes, right? So it puts it in some buffer, and then as scanf is like string scanf is going to be run on the string with this parameter, which is hexadecimal code, because it's supposed to be a hexadecimal code. So this X is a hexadecimal code, and the output of the parser is going to be put into this variable v2. And yeah, this is the message which we saw if we didn't put something that at least resembled a hexadecimal number into the code field. And then there's a check. If v2, whatever we enter, takes more than 16 bits, then it says incorrect code. Otherwise, put it in this. This is plus I, so this is actually an array, right? This is an array of 4 codes, and I'm pretty sure that that these are like one next to the other in memory. So it first fills this code, then this, then this, and then this. So these are actually the codes, right? So this is code 1, this would be code 2, code 3, and code 4. Okay, so I guess something is happening with this random looking data, and the code is passed here, so this looks like decryption. A standard decryption function takes the input data and the code, right, the password, or the key actually. The key is the proper way to put it. So let's call it decryption, or like decrypt. And so what's happening here is that it returns something, and that something is later passed to free. So that means decrypt allocates memory on the heap using malloc. We know that it's malloc because it actually uses free, so it has to be malloc, right? Because you always have to call the function from the same family, so malloc free, or like heap alloc and heap free, and so like, or new and delete. But this case we know is malloc. So it will return a buffer, a new buffer with probably the decrypted content, and that new buffer is passed again to the second call to the decrypt with the second code, and then to the third code to decrypt, and so on. So yeah, at this moment it looks a little scary, because how do we know that the decryption actually was correct? Because for all I know, right, there is no way for us to check if it's correct, but there is an if here, and the if actually checks if this has been correctly returned, like this is non-null value, right? And if it's a null value, then we get wrong code. So it seems that the decrypt function actually does internally checking of whether the decrypted data is correct or not. So there must be some HMAC or well, actually a hash or something like that next to the data. So probably that's what's happening in the decrypt. Yeah, now we can look at the decrypt. Okay, that was actually way shorter than I expected. Well, I would expect. I know the challenge, right? Again, but shorter than I would expect. So what do we have? We have malloc. We allocate the memory based on argument 2, so that is the size. This is confirming that is the size. Then we set it, like fill it with zeros, and then we have a loop from 0 to the size, which does actually XOR and minus. Like this is a homemade cryptography, which is really bad, but that's fine because I don't know. I don't think it's fine, but it's a reverse engineering easy challenge, so that's what to be expected, right? And the v4, what is the v4? v4 is actually initialized with the code, and later on is being multiplied by this value, which is quite funny. So I guess v4 is actually the key, and this line is like rotating the key, or actually like moving the key to the next position, the key stream. So this is the key. This is the initial key, so init key, let me name it like that. This is the size, so I'm going to use a Z. This is the output buffer, so DST, let's call destination. And this is the input buffer, so let's call it source. And I guess we have a pretty good understanding what's going on here. Apart from this, there's a call to this function. We reset something when we call this function. And yeah, and this function is called on the destination, so the decrypted data with the size minus 32. So that would mean what I said before, but there is the data, but after the data there is some checksum of it, like some hash of it, so that when the data is decrypted, one can figure out if the decryption was actually correct. This is a standard way to do it. For example, if you extract a zip file, this is also what is happening. There is the compressed data, and next to it there's a hash of the data. Well, not really a good hash. In this case, we had 32 bytes, so that might be SHA 512 or 256 or something like that. So that's pretty decent. And then we have mem compare, a binary compare of whatever is in v5, which is the output of this function, it seems. to whatever is at the end of the data. So this is the end of the data. Destination moved by the size that then retract by 32 bytes. And this is again 32 bytes for comparison. So it checks if the hash was correct. And if the hash was correct, memCompare returned 0, then the destination buffer is returned, this allocated destination buffer holding the decoded data. Otherwise, it frees the buffer and returns a null pointer. That means that the hash was not correct. Now let's look what is this function. And the function calls some other functions and actually does this, which means it brings the the 32 bits isn't binary, 32 bytes aren't binary, it's actually the hexadecimal representation, lowercase hexadecimal representation, which might be important later on, which is quite funny, because usually you would expect a raw binary hash there, but this, for some reason, is actually a hexadecimal representation, but that's fine. So that means we are left with a 16 byte hash, or 32 bytes, 32 hex nibbles, and there aren't a lot of hashes like that. Well, there are several, but MD5 is the most popular one, I would say, right? So it's probably MD5. Is it MD5? Can we confirm if it's MD5? Let's try to do that. So yeah, let's go here to this function, and there are some magical values here. Now, what I'm going to do, and this is a pretty standard thing to do, is I'm going to copy the value and put it in, like, just Google for it, right? So this is one value, but then I'm going to grab the next value, and yeah. Just two values, and it says it's MD5 implementation, but then it says it's SHA1. So which one is it? Please make up your mind. Let's assume, so I know it's not SHA1 because SHA1 is actually has 20 bytes of output, and we have only 16 here. So yeah, this is the initialization for MD5. So we actually confirmed by looking at the cryptographical constants that this is MD5. Now, if we would want to be super safe, we would go to the next function as well, and there is quite a lot of math operation here, and it actually should, yeah, this is what I was looking for. We might want to check the mathematical operations here, because hey, maybe it just looks like MD5, but somebody played a little with the constants, or maybe it's something else. But we can first, and that's a good thing to do on the CTFs, assume it's a normal vanilla implementation of MD5 and work based on that. If for some reason, whatever you do next, it doesn't work, it fails, then come back to this and check if the implementation is actually correct. If that's well, the other way around is just to call it for some known values and check if the hash is the same. So yeah, we now know how it works, and thanks to that we know what to do. And what do we need to do is actually we need to well, brute force the code basically. You could do some crypto magic actually and not have to brute force the code, but I guess we can either brute force it, or yeah, I would just brute force it. That's probably going to be easiest and fastest. So and to do that, what we do, we will try the code from 0 to FFFF, right, 65,000. And when the decrypt function actually says, yeah, it was fine, but we know that's the right code. Now we could actually do, like, call this function in a couple of ways. I wouldn't really want to re-implement this, but I think I'm going to because this is quite easy. I'm going to re-implement it in Python. So let's just do just that. So I'm going to call it go.py, because why not? Let's make the font a little bigger. Let's do this. And this is the decryption function, right? So I'm going to just copy paste it and translate it to I need this one. Yeah, let's translate it. So decrypt, and I need a buffer, and I need a code. And yeah, I could actually copy a little more of it, but it doesn't matter. So this is the code, this is the initial key actually. and then we create a buffer, but I'm not going to create a buffer because this is Python. I'm going to create a list. So let's just call it DST and then create a list. Or I should actually do like byte array of buff, but of length of buff. Yeah, this is what I will do. And yeah, and then we have this loop. So this is for I in x range as z being len of buff. So we can use as z here as well. And what we do is the destination of I is supposed to be equal to the source of I XORed with the key, and then minus a high byte. No, that's actually high, like in high, right? So minus the high byte of key. So the key we need to oh, in this case it's actually a low byte of key, which is not written there, but it shouldn't matter, but let's do it anyway. Yeah, so this is the low byte, and here if we move it by 8 bytes and actually do this, then we get the high byte. So we had the high byte, we moved it, shifted it to the low byte position, and then we removed all the bits which are not on the low byte position. Cool, so this is it. Then, oh, we need to still like iterate the key. So key is supposed to be equal, what kind of operations are these, by the way? This is AX, so this is a 16-bit register, as you can see here. So we need to emulate the same mathematical operation on the 16-bit register. So let's copy the constant and let's actually truncate it to 16 bits by using this again. Cool, so this is it. Now it has been decrypted, but what we need to do is we need to calculate. So yeah, we know this is MD5, so just calculate MD5. So MD5 dot MD5 of the destination, but without the up to the size minus 32, and we want the hex digest. So this is the actual hash, and the good hash is whatever is at the destination starting from size minus 22 up to the end, and this is the good hash. And I guess we can convert it to string. Now what we are going to return is we are going to return whether h is equal to g, but I'm going to do one more thing here. I'm going to print print both g and h just to make sure that the format is okay, because you know, if one would return capital letters and the other would return lowercase letters, then this wouldn't work, and I'm pretty sure that's the case. Both return lowercase letters, but I still would prefer to check that out. Now I do need to grab the data which is actually being decrypted. Now the data which is going to be decrypted is is this data, and this data, as we can see here, is at this offset of we cannot see that. Sorry. Yeah, let's do it like this. Yeah, this is the offset on the file of the file where the data is located. That would be 4020. So I'm just going to get that data straight from the file. Let's call it decrypt after all, decrypt, because I want to use D for open the Oldskull exe file as binary, and I'm going to read the file, but I'm actually only interested on the data which starts at this location, which is again 4020. And this is the size of the data, right? Yeah, this is the size of the data, so I'm not interested in more than the size of the data. So let's just call it like data size this, and okay. Yeah, so one might say that the proper way to do is actually to seek to that place in the file and then to read only the data you need, but the file is only 44 kilobytes. This will be super fast anyway, and it's not part of the brute forcing anyway, so it only happens once, so it doesn't matter. Okay, so I have the data here. Now here, what I would like to do is, I don't know what I'm actually going to do this here. I'm going to convert this into a byte array, because I'm using it as a byte array here, like in this place, and so it should be like that. So let's try to decrypt it and see what happens. I'm going to try to decrypt the buffer, which is again D, with the key 1234, sorry. And let's go. It says source is not defined. It is not defined because I called it buff, which was a mistake on my part. Here we go. Okay, then it says that the blah 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 byte must be in range, which actually means that here we actually need to truncate it to a byte again, because the result of this subtraction here will not fit into a byte. We need to make sure that, well, this is a byte array, right? So we need to make sure that whatever we assign here, the source of assignment is actually a byte. Yeah, and it says blah blah blah. Yeah, this totally doesn't look correct. So, but that's fine, because we know that it will look correct when the decryption goes correct, so when we get the right code. But I know this is lowercase, and from the code, just by looking at this format, it's not %.to capital X, it's lowercase x. That means it's lowercase hexadecimal number, well, digits, right? So that's fine. And now I can brute force it. I'm not going to print it anymore. Yeah, let's just go for it. For I in X range, the whole range of 16 bits, try to not print it. Like, if it actually works and I want the code here, then please print I and break. Okay, and let's see if it works. It's kind of slow. Let's use PyPy. PyPy is the JITed Python compiler, so it should actually be pretty... Yeah, okay, and we have the code. The code we needed in is 16 bits, so... let's print it as this, like for... Okay. Yeah, I probably shouldn't rerun it, but that doesn't matter. Now, just, okay, so it's 5B42. So I'm going to run the crack me again, and let's see if I'm going to enter anything here, and it's incorrect code format. Okay, we need to enter something here. Wrong code 1, and now let's do 5B42, and it's wrong code 2. That means this code is correct, so we had already brute force this. So I guess what we need to actually do is we need to like have a couple of iterations here. And we do code 1 equals... oh, we need to get the decrypted data as well. So the decrypted data would be, in this case, so it is at H? No, it's not this. This is the decrypted data. Yeah, without the hash at the end. We don't care about the hash at the end. So if... okay, let's change the total. So I'm going to remove this, and it's going to be the result and the data, like the decrypted data. I'm sorry, my naming is terrible, I know, but it doesn't matter anymore. Anyway, so if the result, then we know that the code was I, and we know that, well, the DD will be set to whatever the data is. That's fine. And now we can continue. This is actually going to be DD1, like decrypted data 1, and this is code 1 as well. So this is decrypted data 1, but we are now using decrypted data, sorry, decrypted data 2 here, and we are using decrypted data 1 to decrypt it, but we are assigning to code 2 because we are decrypting, well, whatever is code 2. Oh, we don't need the code, we just need to print it, so whatever. Yeah, let's just do it 3 more times and run it, and we can call it a day. Well, call it a task, I guess. Okay, and 3 and 4. Okay. We actually don't need the data in the end, but like at the end, but that's fine. Okay. First code, second code was actually quite small. That's cool. That's 1 free CC. I'm going to check if there's any question. Oh, there are some questions. So one question really fast. What do you think about secure boot from security perspective? Does it help really? If correctly implemented, that's a good idea to have. Otherwise, there is this so-called evil maid attack, which is somebody, you know, you leave your laptop in the hotel room and then another party comes in, like unscrews your hard drive, puts it in their own computer, installs a more nasty boot sector or bootloader, right? Puts it back in the computer, screws up the screws on the hard drive, and leaves it there, and then next time you come back to the room, you try to log into to the laptop, everything works, but now you are backdoored, right? So this is the evil mate attack. So instead of like a real mate, an evil mate comes into your hotel room. Obviously, it's true for every physical scenario where you lose sight of your computer and somebody else might have access to it. And it actually really works really well on penetration tests and so on, if you can do physical stuff. So it's a real threat, it's not a made-up attack, right? Yeah, and secure boot can help here because the idea is that in this case, BIOS would check the checksum of the boot sector and would say, hey, this is actually have been tampered with, so I'm not going to boot it, I'm going to display this huge warning to the user. It's actually a little more complicated because the BIOS, like, maybe the BIOS was replaced, right? So who's going to check the BIOS and so on? And maybe it wasn't the boot sector that was replaced, but some other part of the system. So the idea is that it's going to be like pardon the pun, chain of trust, where everything which was happening before checked the next step. So each step checks the next step, whether it's actually correct and so on. And then you need like the to store securely the hashes, and that's done in a trusted platform module usually. So yeah, I think it helps. It's pretty useful. That's a quick answer to the question. Though I'm not sure if it's implemented in many places. I would look at Cube's OS. Cube's OS, I'm pretty sure they implement it in the best way possible. At least in the operation system level, because, you know, on the BIOS level, that's not really in the hands of operating system developers. Okay, so we have this. Now, we still don't know the code, but it says the wrong flag. So that means that the codes are correct, and that's fine. What we have at the end here, and what I can actually like just, yeah, I don't need this anymore. I can replace my brute force with the actual keys right now. Because I need to run it once more to actually dump the executable, because I forgot to do it in the first place. Okay. 1C33. Yeah, so a correctly implemented like secure boot should actually also detect whether a PCI Express device, for example, was inserted into a slot or changed. Yeah, you probably know that when the computer initializes, then like x86 code is being pulled from PCI devices, so when it's executed by the BIOS. At least that was what was happening before. I'm not sure about UEFI, but yeah, BIOS just pulled, like, for example, a driver, a BIOS module from the graphical card, so it could initialize the card before the BIOS went on. So yeah, if you could like replace that piece of code on the graphic cards, then I'm not sure that's actually part of a trusted boot. It would have to be checked. Okay, it works now. I have to just dump the data, so open dump like checker.exe, write binary, write dd4. Okay, perfect. So we have a checker now, which is dumped, which is 19 kilobytes. So let's see what's that. I'm just going to open it in IDA. Okay. Okay, here we go. Let's see what magic waits on the second stage. And could you wait? Oh, wait, I clicked on the wrong IDA. Sorry about that. It's again a 32-bit binary, so I'm going to open 32-bit IDA just so stuff works. Okay. And this is what's happening here. Some function is called. What is going on here? Oh no, this is like a part of a compiler prologue, I think, in main function, so let's ignore it. Then it's checked whether the argument is 20 bytes. So it must be 20 bytes, otherwise it returns, and then it checks whether the bytes are equal to something, XOR something. So I guess this will be the flag just XORed by this value, so let's see what's there. Well, we have some bytes here. I'm going to copy the bytes, and since I already have this file opened, let's just like move to the beginning. And let's yeah, grab these the values because I care about the values. So these are the values, then what does it, what? Okay, so this is, okay, and this is a duplicate value, 2 times this value, so let's do this 2, and 2 times this value. So I guess the flag has some duplicate characters in it. Okay. Okay, now what do we do? What do we need to do here to make it a little saner? I guess we... let's just do this. I'm going to remove the leading 0, I guess, and I'm going to remove the H at the end. Or no, let's maybe add actually an X to it. Okay, so let's add an X here, and yeah, that's properly formatted data. So this is the flag, and this is a list, and we need to output, so print the flag, which is actually, and we create a character out of X XORed with, so what was the value again, because I already forgot. I think it was, 8F, I was going for F8, but whatever. In, for X in the flag. And yeah, then we can like comment out the rest of the code already. So okay, it's commented out. Now we can run it, so go. And yeah, that's it. We have the flag. DRGNS, like Dragon Sector, way too easy. And but that is it. We can try it. DRGNS. Okay, check. And yeah, well done, but you know that. Yeah, we know that. So that was the simpler task, and it was solved again by the top teams in like 19 minutes or something like that. We can actually verify that on the website in a second. So yeah, let's go here and let's go to... Oh, I can actually submit the flag. Yes. Okay, that's the correct flag. So on the scoreboard, sorry, on the challenges page, oh, it's already disabled. Otherwise, this would be like in green, and this would be green too. Well, whatever. If we look at the activity log and we scroll up to the beginning of the CTF, yeah, so it's 13 minutes. The CTF started at 2 p.m. and at 2 p.m. 13 minutes past already. This team solved it. So that's quite amazing. So this was the easier task. Now the harder task, I'm not going to solve it. I'm going to tell you how it was, how it works, because just explaining how it works will take like 45 minutes. So yeah, I'm not going to show you how to solve it. Again, please go to my blog and to the write-ups, which I've linked here by KrzaQ 1 from P4 and Daniel Lee, because they actually did really good job on the write-up. KrzaQ's write-up is a little shorter. Daniel is really verbose, really goes into the details of how everything works. So I'm going to show you how it's made, not how to solve it. If you want to solve it yourself, then you probably should, should like not listen to the rest of the stream, because there will be spoilers, but well, same for this task, right? So let's start by downloading it. Again, as I told you, there is the source code is included in the download package here on my blog. So yeah, and I'm going to extract it. What happened to my console? Oh, I already closed it. Okay, never mind. So let's open it again. Here we go. Okay, so yeah, there are two directories, right? The first one is files for the players, and there's one file here called chains. I'm going to extract it. So yeah, and it's extracted now. And as you can see here, it's actually a bash script. This is the standard dynamic loader for Linux, which is used by most applications, and a set of libraries. And also this, which is an ELF file and a README file. So we can start by reading the README file. It says run go sh. If it doesn't work, retry on Ubuntu 17. But you do have to use gosh script. So let's see what's in the gosh and task find the flag. Yeah, thank you, Captain Obvious. Here. This is what's happening here. It actually like just sets the executable flag to these files. I don't think this is required, but whatever. And then it runs the dynamic loader with the library path being set to the current work directory. That means the application will look in the current work directory for the libraries, and it because by default it looks in the system directories. Yeah, and then it actually just runs the application. So like there's little difference between running, like this actually is the same as setting LD library path to dot and then running something. So if you're more familiar with the syntax, then that's fine. But the way it's done here is actually more portable, because it might mean that this might work actually on a different system than Ubuntu, because the loader is compatible with the libraries and the libraries are compatible with the application. That isn't fully true because, for example, libc uses system libraries, loads dynamically system libraries for handling DNS resolution, because there are functions in libc like get host address and so on, which do use DNS. And these use system libraries which are dynamically loaded, so not all libraries are actually here, and I'm not sure if that's possible for all the libraries to have there, because something like DNS resolution is actually really system dependent, because that might use the system cache before actually going to DNS servers and so on. So that's why the C library does it dynamically and doesn't actually implement the DNS resolution itself. So let's run it, but I do need my Linux console to do it. So here we go. Okay. And yeah, okay, it says, welcome to Chains, connecting to master, checking required libraries, and it checks pthreads, so we are to expect threads. Looking good so far, but we'll do some more checks, and when we go back, there is actually this not fancy graphical art. I'm sorry, I couldn't find the proper ASCII art for a chain. Yeah, and you have to put the flag here, and let's put anything, and it says thank you, now please wait a second. So for some reason checking the flag actually takes some time, and it says no lag. Okay, so let's before we get to the source code, I'm going to show you the binary. This is, by the way, if we do a file on it, so let's do file on chains. It's a 64-bit binary. By the way, we can try to run it without using the Go script. So it says everything is fine, and then, yeah, it seems to work anyway, but it says at the end, no debugging, go away. I guess if we run it, again, it says no debugging, go away at the same time, but we are not debugging it, so what's up with that? But we are not running the gosh script either, so it means it actually really needs to use these libraries, which are here. Perhaps it detects that some of these libraries might be modified, might have some special function saying that, yeah, this is me, this is the real library which you want to use, and the system library which would be used by default do not have that. What you could do as a CTF player, you could go like do MD5s or whatever, like SHA checksums of it, and put them at Google, like Google for them, and see if these are the default libraries from the Ubuntu 17.10, which is mentioned in the README file. If these are the default libraries, then you know they have not been modified because, well, the checksum matches, right? And actually, yes, these are the default libraries. They're not modified in any way, so something else might be going on here. Now, let's look at the binary in IDA. Okay, it's we have to go here. So this is the main function. The main function is actually checking if master host is set, and if it's set, then it overrides this pointer, which points now to chains of trust felina.pl with some whatever is the value of this environment variable, and then it calls the function, this function. Okay. Now, oh, by the way, if you cannot find any hashes for this at Google, let's actually try it. So let's do like sha1 sum, and let's see if we can find anything. No, it doesn't find, so let's go for 256. Okay, I don't know. For all I know, maybe my workstation is backdoored because these files are from my workstation. Yeah, that's annoying. But if you would actually get Ubuntu 17.10 and compare the files, these are the files. So maybe I did expect the hashes to actually be Googleable, but it seems they are not. So sorry about that. That doesn't matter. These are not modified files anyway. So what is in this function? And I guess the most important part here is that something is going on with the host. This is the host, right? So we know this is the host. And if we go here, it's actually like gets host by name and then calls some other function which does, what does it do? It calls connect. So it's a TCP, it is TCP by the way, TCP connect to, well, some aforementioned host, which is like chains of trust felina.pl, to, I guess, this port. This would be the port. Yeah, this is the port where it connects to. And we can double check it by doing like just encoding there. Chains of trust PL 6769. And yeah, we get connected there and we are immediately spammed with some binary data. So okay, we connected there, and then what else is going on here? It says master disconnected. So what is this function? This function is actually receiving data from, well, from the host, which makes sense, right? Because we did see that the host is sending the data. So this is like receive the data. Let's go like plus, and then it allocates memory with 7 permissions. 7 is actually read, write, execute. So it allocates enough memory for the data which it receives, and then what's happening then with the address? It also receives some more data, it seems here, and then it actually calls this address. So it receives a shellcode from the server, and then it calls it with some arguments, including the byte it received here. What is this receiving? Oh, I know. This is receiving the size of the data, and this is receiving the actual data. Yeah, that makes sense. So this is the size. Yeah, this is the size of data. Okay. Yeah, and there's some byte passed and some pointer. And if we look here, it's actually nothing is initialized here, but if we go to the place where this is initialized, we will find out that this is a function table. This is what I called an API table. So there are some default C functions like puts, printf, exit, dlopen, and dlclose. Dlopen is, by the way, for it's a function which is the same as load library on Windows. So it opens a dynamic library, and then you can get a function from the dynamic library. And there are some other functions as well, which might do some stuff, so we might have to analyze them. So okay, and this is everything which I just described is done in a while loop, while some other byte is not set. What says this byte? I guess this is... sorry, what happened? I want to... Oh, yeah, the byte is set here. Sorry, I misclicked. So yeah, this is some function where the byte is set, and if we look where this function is referenced, it's actually one of the API functions. So once this function is called, then the loop exits, but before that happens, it actually, it actually continues, right? So yeah, now what you could do actually at this point is run Wireshark and see how many shellcodes are being sent, and like dump the traffic, and then dump the traffic again and again and again. What you would find out is that there are 97 payloads sent. Yeah, like 97. Like this kind of 97. So that's quite a lot. Furthermore, you'd find out that each payload every time is different. As in, if you would compare the bytes, the beginning will match, but after the beginning there is some random looking data, and that data always changes. And apart from that, quite randomly between the shellcodes, some other data appears. So what's up with that? And this is actually what I've, by the way, explained here. This is everything which is in this binary. There's nothing else in this binary. So yeah, the flag checking is not in the binary, it's actually in the shellcodes. The shellcode which before told us no debugging, so yeah, let's reproduce it. Yeah, no debugging, go away. This is also a shellcode. This wasn't in the main binary. So what you have to do now is you have to basically automate, create a script which will either like chat with the server or act as a proxy, because again you can set the environment variable so you can act as a proxy, or like do some other stuff to dump the shellcode and then analyze the shellcode. Now let's grab a shellcode so I can show you how it's actually how it's done, what's going on there. So I'm just going to dump the first one, which is sent immediately by the server. Okay, it's dumped now. Our dump file is 4,000, like 4 kilobytes. We know that the first 4 bytes are actually, yeah, let me just show you that. We know that these 4 bytes are actually the size. So if we look here, this doesn't make sense because I'm not switched to Intel. Okay. Yeah, so this is the size, which doesn't make sense. Doesn't make sense either. It's quite a long shellcode. I'm pretty sure the shellcode is actually smaller. Maybe this is the size, or maybe I'm mixing something up. But there should be the size at the beginning. Anyway, doesn't matter. Let's put it in the dump. No, it should be 4 bytes. Sorry, let's put the dump in IDA. Okay, let me try and define this. Yeah, okay, here we go. So yeah, there's some code which is run at the beginning. I think it begins here because this is the size. And what's happening here is actually pretty easy to see once we do, I think, yeah, P. Okay. It's, I think it's actually in assembly, it's even better visible. So let's switch to this, to the graph view, right? It initializes something, there is the argument, initializes something. And then in a loop, it, I wonder why it actually cut here. I have no idea, whatever. Yeah, then in a loop, it takes a byte, puts it in AL register, then does some mathematical operations or binary operations on that. But all of these operations are actually not losing any data, any entropy. They're all mapping 1 to 1. So that's XOR, rotating, adding, subtracting, well, and NOP, I guess. So there is no add, no multiplication, which might actually like truncate some bytes, no division, which would get rid of some information. And once this is done, it actually calls it, like calls the decrypted data. So it's a self-decrypting, self-modifying code which decrypts itself, then calls itself, and then at the end actually removes itself from memory and returns to whatever. So now to make matters worse, this part was actually randomly generated by the server. So each time you requested a payload as a shellcode, right? The server would randomly generate the list of instructions and the constant values here, and would encrypt the actual payload with that and send you the bundle. The decryptor with this algorithm randomly implemented. I think this is called like polymorphic code, by the way, and it was a pretty popular anti-RE technique. Like for example, Yoda Protector and Yoda Crypter used this technique for obfuscating exe files. So this is the same idea, just randomly selecting an instruction and selecting a key, and on the server side doing the exact opposite of it, and generating the code that does it. So what you would have to do is you would have to automate decrypting based on whatever code is here. And after that, after decrypting the data, you would get the actual shellcode, the actual payload. So once you get to that, you would understand that there aren't really 97 shellcodes. There are only about 21, 22 shellcodes, and each of them doing random stuff, but you can group them in several groups. And this is where we go to the source code to make stuff faster, because you would actually have to reverse engineer them. And they're not long, but let's just look at the source code. Okay, so let's actually do this. Source code, and go to source, go to server, and go to codes. And yeah, these are all the shellcodes. Now, the shellcodes could be grouped in, I guess, 2 categories or 3 categories. Yeah, let's go for 3 categories. One is actually relevant to the flag checking. The other one is anti-debugging, anti-reverse engineering shellcodes. And the third one is like miscellaneous. It's actually like supposed to either don't do anything interesting or be called when the program is supposed to exit with an error message, or like be a proof of work that to make sure that the shellcode is actually being executed and not being skipped by the proxy or something. Now each let's start with, I guess, something which doesn't do too much. What would be... Oh, yeah, I know, checking the libraries, this one. Yeah, this is what's being called first, the main. The API is going to be passed in the first argument and a chain value as the second. Now, the chain value is actually a value which is calculated by each shellcode. It's calculated both on the client side and on the server side at the same time, and then it's being compared. If it doesn't match, then the server is supposed to disconnect the client. Now, yeah, and by the way, each shellcode has a different mathematical formula which calculates the new value, but it's so it takes the old value, it takes the new value, so the old value, the challenge, which is the new value, which is actually being received from the master, from the server side, right? And then it calculates it, and then it sends the new value to the server, and it returns the new value to be stored by the main binary and passed again as the chain value to the next shellcode. So if one of the shellcodes actually does the math incorrectly, then the server, well, the same thing, the server says, yeah, it's like the math doesn't work out, you're probably doing something fishy, because a real shellcode, a real chains of trust would never do that. So it kills the connection. At least that's the idea, because I saw that Daniel was saying in the write-up that that doesn't really happen, because he always gets the next shellcode. That being said, there is a shellcode sent after that, which is a shellcode which actually kills the program. So we might both be correct. And I'm pretty sure while testing I got killed by it, like my process was killed by it multiple times, so it works. Okay. So yeah, in this case, the actual work is going to be done in the worker function, which is here now. The main is expected to be at the beginning of a payload, that's why it's put in a different section. And I actually have a linker, had a linker script to formulate the binary. Yeah, this is a linker script. It basically says how the binary should be outputted. And binary means no headers, like no ELF headers, no PE headers, just the code as it's described here. So the start sections go first, then the text section, and then the data sections. And an end section, though I think I used it for some binaries in the end. So yeah, this was first always emitted in the shellcode, and then we had the worker. The worker was actually, like in this case, the shellcode wasn't doing almost anything. It had a list of libraries, and it was calling DL open on all of them, and it was printing like missing required library if that would happen. This was supposed to just like show the players how something easy works as a payload. And this was always sent as a first shellcode. And you know what? I can actually show you. Chains master. Yeah, this is the master, the server side. Yeah, this is the list of stages, because the shellcodes were sent in stages, and there was always sent, this pre-check was always sent first, so the players don't have to deal with anti-debugging shellcodes at this moment. Yeah, and then the next thing we just sent was from the group called proof of work, and the proof of work was actually like 4 really simple, really almost identical shellcodes, which looked something like this. They were just meant to be to check if the code of the shellcode is actually being executed. So yeah, this is the challenge, and the math again is different, but this is what was really going on. It sent a magic to the server, and then the server replied with a challenge value. And the challenge value there was some super simple mathematical operation done on the challenge value, and the server side then checked if the value which was being received from the client, only 1 byte by the way, is correct. And if it is correct, then continue, otherwise fail and bail out. So this was sent, 10 shellcodes at random were sent like that. And again, each shellcode was had the randomly generated obfuscation, right? That being said, that was actually calculated while building the challenge. As in, while building the challenge, each shellcode was built in 1,000 different variants of the obfuscation. So it doesn't. The server side actually just used the cache for that. Didn't have to calculate that each time the player called, because otherwise it would be quite slow. And after the proof of work was done, ptrace was called, like ptrace shellcode. And ptrace shellcode is one of the anti-debugging shellcodes. What it does, it calls ptrace. There was a live stream some time ago about me using ptrace, right? For nanomites on Linux, so you might be familiar with that. If you're not, then just go back to that live stream. And yeah, if basically if a debugger is attached, then ptrace 0, which is ptrace me, will return -1, and that means that there's a debugger present. But I did actually another check later on. I will show you. Anyway, after this call, if it doesn't fail, then the next ptrace call will fail, which is important to remember. Now, yeah, then again, 10 different shellcodes, 10 random shellcodes from the anti-debugging group were called. Sorry. Yeah, and this is the anti-debugging group with some shellcodes. I'm just going to show you them. I'm just going to tell you what they're doing. Ptrace 2 is actually making sure that the call to the ptrace fails at this time, because it's known that the call to the ptrace that succeeded was done before, and only one call to the ptrace me, is going to succeed in a process, unless the process is detached, right? But it wasn't in this case. And then it actually also checks whether the error number in the environment variables, in the global variables is set correctly, just to be sure that somebody doesn't spoof ptrace, or actually has to spoof both these places. Environment 1 and environment 2 actually just check if LD preload is present. If it is present, then go away, and it's being checked once by using the API and once by using the environ global variable. There could be a third way, which would check the proc self environ file, like a sudo file, and see if LD preload is there, because LD preload could be used here to inject functions, and I didn't want that to happen. Well, actually, I wanted the players to beat this mechanics and then use it, right? Then parent 1 checks whether the parent is not called GDB, or actually doesn't have GDB in the name, and this is done by going to proc self, to getting the parent PID and going to proc parent PID, and then I think reading the link from the exe file. Then the libs1 was checking the checksums of all the libraries which were in this file, so in the directory. So all the libraries, which were not all, most of them, and the executable file were actually being checksummed. So if you edited the main binary, this would be detected by this shellcode. And exa1 is oh, so sorry, the libs1 actually checks the libraries, and exa1 actually checks the checksum of the binary. So then we moved on, and it checks libs2, which I don't remember what oh no, sorry, I'm actually mixing things up. Exec1 checks the hash of the binary, and libs2 checks the hash of the libraries. But libs1 checks whether the libraries which are being used by this process are actually the libraries in the directory of the process. And this is done by looking at the proc self maps file, because if we do that, right? So if we do like cat proc self maps, apart from the addresses, which is usually what we care about when exploiting stuff, there are also the paths here. So yeah, one can just like check if this is the same as the path to the binary as being given by read link self. Sorry, proc self exa file, or just exa. Yeah, yeah. So it checked if this string is equal to this string. If it wasn't the same, then it said, yeah, no debugging, go away. So yeah, then display was actually the main menu. It was the part which asked you to enter the password, then it stored the password somewhere in memory, and then after checking some global variable for some time, when the global variable was set, it outputted some text and exited. So that was the display. Now, the whole idea with everything else is that it was like a virtual machine of an FPGA-like device. I will get to that in a second. One more thing which I didn't say about is thread noise. Thread noise was another shellcode. I'm going to show it to you just because there's an important piece of a puzzle there. It actually doesn't do anything, but there's a mechanic which is used there, a mechanism. Yeah. What it does, it actually creates a new thread and then it sleeps. This is just to make some threads in memory so that one doesn't know which thread to look at. But not a lot of threads were made, just a couple of them. However, what's actually going on here is it creates it's like this. Because as I shown you at the beginning, a payload decrypts itself, runs itself, and then removes itself from memory. Therefore, if you start a thread and then the thread which started you is still continuing, then it will remove itself from memory. So you don't want that to happen. So what you need to do is you need to allocate another region in memory, copy all your code there, and then jump there to that code and continue execution from that code, because that region of memory will not be removed. But the original region of memory where you were running will be removed in a second, right? So that's why we had to get the start address and the end address. Now, usually this is trivial to do, but it turns out that linker, the GCC linker, doesn't support position-independent executables if not going for ELF files, and I went for binary files here, right? So it just couldn't output the correct code. So I had to do workarounds, and I actually found two workarounds. One was to just do an assembly, just insert the correct assembly yourself, basically. So if it, and yeah, you might say, hey, Genway, what are you talking about? The linker doesn't change the assembly code. It's the compiler that generates the assembly code. No, actually, the funny thing is that when it comes to position-independent executables, the compiler generates a code which has some code which do something, but actually the linker replaces that code with a relative LIA, for example, to RIP. So yeah, the linker changes assembly instructions, which is quite crazy, but not something you would expect, right? And yeah, and the linker wouldn't do that, and I like spent 4 hours, I think, debugging this and thinking of workarounds. I wasn't too happy with that. And the other one was actually just going for magic. I put a magic value at the end of my code, and I scanned the code from the beginning to the end to that magic value. And when I found the magic value, I knew this is the end of the code. So the magic value is being put here. As you can see, I'm using this end section and I'm putting this magic value there. it's quite funny to, you know, kinda. It's a funny problem that you cannot put this value in the code, and if you're doing a comparison looking for this value, you'd have to put this value in the code as well, because you will find the value in the code instead of the value at the end of the code. So that's why the value is actually repeating for 1, for 1, for 1, for 1, and I'm just counting the number of subsequent 41s being there, and if I find 8 of them, then that means that I'm at the right spot. So yeah, it's like a, what was it called? That's a name for applications which output their own code. But I'm missing the word. Like, please help me out on chat. Yeah, I'm missing the word. Anyway, yeah, so this is like this kind of an exercise. And then when I have these addresses, I just copy the code and, well, I allocate it, like using mmap, I copy the code, and then I span the thread starting from the worker address, which is, again, this function. So this is what I had to do. And yeah, the looking for the signature wasn't supposed to obfuscate the code. It was actually a workaround for the linker. So sorry if you were annoyed by that in the code while solving the challenge. Quine, thank you, KrzaQ. I was thinking of twine, but it's quine. Yeah, thank you. Yeah, the CTF is over. The CTF was over on 2 p.m. Switzerland time in Sunday, so a couple of days ago. Okay, so the rest of the yeah, this end chunk just like sleeps for 5 seconds and continues, and this is just a timeout, a complicated way to do a timeout. Now the flag is actually checked in several places. So display gets the input but doesn't really check anything. RAM is this is called database in most write-ups I saw, like both write-ups I actually saw. It's called database. It was actually a RAM device, a RAM-like device. Then APU, which is an auxiliary processing unit. I think KrzaQ actually called it a TP, sorry, not a TPM, like a HSM, like hardware security module, which is also a good name for it. Then there are 3 CPUs which were doing various stages of computation. It looks like a complicated device, but actually the implementation was super short. There wasn't a lot of code. Now this was connected together, and I'm actually going to use KrzaQ's photo, because he did draw a graph of how it's why is it smaller when it's okay, never mind. Yeah, so yeah, there was this was, I guess, the RAM where everything was stored. This was the display, and these were the 3 CPUs, and these were the 4 auxiliary processing units. So it went like this. The display put the flag somewhere. Then the first CPU took the flag from that somewhere and put every 4th letter in the first RAM bank, every 4th letter plus 1 in the second, and so on in the third and the 4th, and then started switched on a flag in the auxiliary processing units, which did something like, I don't know, like some XORing of the data or something like super simple math. We can look at it in a second. And once the APUs were done with XORing the data which was in the given RAM bank, they told that to the CPU, and the CPU said, okay, I'm shutting down now, but the CPU number 2 will take over. So when the CPU number 2 took over, it did some XORing again, I think, or something like that. And then also said, I'm done, and then the last CPU took over. And the last CPU actually grabbed all the data, or maybe that was the second CPU, doesn't matter. Either the first CPU at the beginning or the second CPU grabbed the data from all the RAM banks and put them only to the first RAM bank. So all the data was now in the first RAM bank, but it was again XORed, or some other funny crypto was done on it. Then it calculated the hash of each value, which was quite funny. The hash was like homemade, super simple, of each value. And then it was compared to a list of constant hashes. So what you had to do is you had either to brute force the hash, and it was only a not even 16. I think it was depending on how much math you wanted to do. It was either 8 bits of entropy for brute forcing or 16 bits of entropy of range. So not like super fast brute force. Or you could actually do some crypto magic and get the value, which was the pre-image of the hash as well, quite easily actually. And then after checking the hashes, if they all matched the hashes which were written down in this shellcode, it would communicate again with the input and tell it to display either, yeah, this is the correct flag, or no, this is not the correct flag. So let's look, for example, at the implementation of the APU, because that actually does something. Okay, so yeah, this is basically the whole APU. As you can see, there is almost nothing here. There were a couple of functions called RAM load and RAM store, which I was using. If you look at the function, if you know some Verilog, if you know some FPGA, you will be like super familiar with what's going on there. If you're not, that's an you can figure it out. It was just like setting a flag to tell that the address is ready, then waiting for another flag in memory to be set, to know that the data is ready to be picked off, and then picking up the data from the actual RAM. So it's like it worked kind of like that. It was just setting variables into different threads. Yeah. So what's going on here actually is it waits. It's powered off initially. And by the way, I'm using here this like structure now. There was another funny mechanism implemented, is that the shellcode, while initializing a given device, right? Like for example, the APU or RAM or whatever, allocated memory for this structure, which had held all the controls for this structure. I'm going to show you that as well. Here we go. So for example, for the APU, this is not the file. Command CH, I think that's this one. Yeah, that's this one. Okay. Yeah. So yeah, for example, for the APU, this is the structure. It's like a pointer to the API, then a boolean, whether it's powered off or powered on. That's actually called enabled usually in Verilog, I guess. ID, like which APU is it? Is it the first one, the second one, or the fourth one, right? And then a pointer to the structure, which is called a RAM port, which is actually an interface to the RAM, to operate on the RAM. And if you wanted to operate on the RAM, what you did is actually, this is RAM port. You inserted the address, then you set this boolean saying that the address is ready, and the other thread, the RAM thread, was looking whether the address is ready. Once the address was ready, it determined whether write enabled is done, whether you want to read from RAM or write to the RAM. And if you wanted to read from the RAM, it fetched the value and then it put it in the data. As you can see, it's by the way 16 bits per cell, so it's not typical 8-bit RAM, right? It's 16-bit RAM. Yeah. And then it set the data ready, so your thread could actually monitor whether the data is ready and then read this variable. And there are quite a lot of M fences and like other fences around, so I wanted to be sure that nothing is reordered. I was pretty sure it would work without it, but just to be sure, I didn't want any reordering to happen. So yeah, and RAM load does exactly what I just described. So, while the device was off and some value in the RAM was not set, then it slept. And then it was suddenly enabled by the first CPU, right? So for 8 cells of data in RAM, it actually loaded the data. And then depending on its own ID, it either like multiplied it or did some funny math or did like an XOR or did some subtraction, and it put it back in place in RAM. So this is all it done. And we could go through all the other devices and look at the math, which is there, but I can show you everything written down in one file, which is, where do I have it? Oh, I know where I have it. I don't have it here. So give me a second, because I actually have it in my work directory, which I used for testing. So I do need to find it. So no. Here, no. No, it's here. Okay, here we go. I'm sorry for that. Yeah, so this is all the math which is actually going on to calculate the flag. So we start with the first CPU. This is the flag, by the way. Yeah, so the first the CPU actually put like the first letter went to bank RAM bank number 0, 1, 2, 3, 0, 1, 2, 3. So every fourth letter went to the same bank, and this is what's going on here. Then the APUs took over, and the APUs did this funny math which we just saw, and when they finished, the CPU to actually exert with this value the data which was there for some reason, and then put everything in RAM 3. So this actually explains that the CPU number 2 put the data in one RAM bank, and that was 3. So again, all the data was in the same place, in the same RAM bank, and then CPU number 3 hashed whatever the value is. So it's a hash of a 16-bit value. Don't expect too much entropy there, right? And yeah, and it put it in the hash buffer, and here I'm printing it, but obviously it's being checked in the real implementation. And yeah, this is the hash itself. It's like totally basic, totally easy. It uses some constants based on whatever you gave it. Oh, actually the index position and rotated data, and that's it. I mean, this is like super simple math. So what you had to do in the end to solve it, you had to reach to this, and I either had to brute force it, which was one way to solve it, or you had to do some simple math to get back the letters and in the end get the flag. So yeah, this was a flag, and if you do everything right, you would see the happy solution. Okay, so let's go to client. Okay, so let's run it and enter the flag. And we wait because it's actually calculating. So the math isn't CPU intensive, but thread synchronization is laggy because everything sleeps not to waste CPU cycles if there is no data ready. So it sleeps for like 5 milliseconds and then checks if something is ready, or like sleeps for 30 milliseconds and sees. So that's why it's so laggy. It's not a lot of math, actually, not a lot of calculations. And yeah, that's basically the challenge. Now, I guess the most interesting parts of this challenge were, yeah, I mean, as soon as you got the automation done to get the shellcodes, that was where the easy part began. And there were multiple ways you could get the flag. So yeah, it was basically the idea behind this challenge was to make the players automate retrieving the shellcodes. And I think I succeeded based on the right types I read. So yeah, that's it. I can show you how the task was, how the obfuscation was built. I actually used, oh wait, obfuscator is in another file. This code is very available in the package. Yeah, this is the code template for the obfuscator. As you can see, is like payload length here, and then the obfuscation code here. All the other code was the same for every for every payload. Now the obfuscation code was generated here. Yeah. So these were the operations. Sorry. And the operations were, yeah, they were chosen like 20 operations, num was 20 by the way, were chosen as at random, and what I got was the name of the operation, the name of the instruction, and a function. So I added these functions to to this. And why was it a function? It was a function because I needed both to create a string, like assembly representation, so I could compile it later on using a keystone assembler, right? And I also needed to calculate it the other way around while on the server side, while building, while encrypting the data, because, you know, it's like decrypting and encrypting are actually like mirror operations. So yeah, that's why I needed also a function. Python is like really, really nice for this kind of code. It's like, it was super easy to write this. Yeah, in the end, awesome. Yeah, Keystone was assembling the code, and that's it, and that's how the payload was generated. If you're wondering, all the payloads, all the shell codes and all the variants were actually taking 300 megabytes of space on the server side. So if you want to run the server side, you have to build it yourself, so you have to run the makefile. And that's it. So that was the task. Again, if you were lost at any point, just go to either KrzaQ's write-up, which is a shorter version, or go to Daniel's write-up, which is the longer version. It's really well explained here from a solver's perspective, right? Because I have an author's perspective. I know what's going on, but you can see how they looked at it as well. So I really recommend looking at it. Okay, and I think that's actually it for today-ish. Let's do some questions. I kind of show you the layout. Yeah, I'm going to like use 3 minutes to show you the layout. The idea was basically, like, I don't know if you folks ever done any web design. I've done some. I'm not a professional web designer by any means, but like all my blogs and so on was like even the layout for this live stream was. Usually I at least tweaked or coded in CSS and HTML. Wasn't really coding, but okay, coded by me. So yeah, so I sometimes do it, and I also handled the web design. We previously had, in previous years, had a Bootstrap one. So this is actually modified Bootstrap layout, and yeah, I went about it like this. I basically written down everything I wanted about the layout to show the graphic artist which I was going to be hiring, and everything about the website, all the art which I needed. So I needed, for example, this logo, right? But I also needed a version which said like 2018 and actually had a huge dragon here. This is what you could see on the Twitter of Dragon Sector. So if we go to yeah, this is the larger art, right? Then I needed tiled art to do the fancy borders. Then I needed tiled art to do this banner, or tiled art to do this, or tiled art to do this. Yeah, and then after writing this down, including, you know, the resolution of how large should it be, what the style should be it be pixel art, should it be like high-res pixel art, what colors would I want it to be in, and so on. After writing that down, that was, I think, like around 2 pages, 3 pages of document, I went to a really awesome forum where quite a lot of pixel art designers are hanging, and like showed them the document and asked who would be interested in making the layout for, like, given the budget that we have, right? And actually quite a lot of artists replied, and I was quite positively surprised. And in the end, like, I looked through their portfolios, they were just amazing. Like, these people were awesome. In the end, I picked one person who made this, and it's actually quite. If you never worked with a graphic artist, it's worth doing it at these ones. I actually lived with a graphic artist for several years when I was on my university, so I kind of know how they work. But it's yeah, it's actually quite cool, you know, to see concept arts and so on, and then say which direction to go and so on. So yeah, after that we got the graphics, and it was about putting it together. I spent, I think, around 10 hours putting the layout together, and these were usually, or maybe even more actually, I think it was 16 hours. And these were usually like after midnight hours, so I didn't get much sleep last week. And yeah, in the end, this is what we get. There are some fancy features which were somewhat working during the teaser CTF. For example, if a new news was going to appear, there was a function which was called play news. Okay, and yeah, this animation appeared. So like both the news here was shining red and this was shining red, and there was like a snippet of the news here. So if you clicked on the dragon or clicked on the news, it actually moved you to the news section. So for example, if a task has been fixed, or if a new task has appeared, and folks didn't refresh the website, didn't check, so there was some indication for that. So it was quite a lot of work, and I also learned quite a lot of new HTML and CSS. For example, it's super easy right now to do tiled-based borders for anything, for like a div. Tile-based meaning that let's inspect this. Yeah, you basically do a border image, and this is a thing I didn't know existed. And I've started with doing a table with 9... Yeah, table, because divs are super annoying in such cases, so table is easier to do. And like nobody looks in the source code anyway, right? Yeah. And then I found out that, yeah, like just supply graphics, which is like 9 tiles by 9 tiles. So this is, yeah, the top center part, bottom center part, the corners, and then border image, this, and that's it, done. So I was quite happy to learn it. So yeah, I kind of learned a few things as well. I've seen that people really like the layout, at least the ones who commented. I also, after like 10 hours, I also started to like it. So yeah, it was fun to make as well, as in like design, then work with a graphic artist who is actually amazing and done all the art and putting it together. Okay, yeah. I just wanted to brag about it because I'm really happy about it. So let's move to the questions. Okay, you should see the questions there. No, wait, there, because I have mirrored image. So let's move here, and the question should, yeah, it is there. There will be no mission. I'm in like I have a huge backlog with missions, with mission solutions and so on. So we're kind of on hold now. We might get back to mission at some point. Okay. Have you ever tried to do something with a TPM? Actually, no. I actually even bought an additional TPM for my server, like home server, to play with it, and I never got to it. So I hope to play with them at some point. What is the whole Lojax thing? I have actually no idea. I don't know. Sorry. How about making a whole Win API stream? Seems you are experienced Win API user. Yes and no, as in I did use quite a lot of Win API back in the days. So when I was in the university and so on, I have no idea about the new Win API and how people currently create windows and so on. I'm pretty sure they don't do it the way I do it. But we could make a general stream about Win API. That's actually a really good idea, so let me know that. Okay. Yeah, like just knowing the basics and how things work in Win API helps a lot while reverse engineering, so we can try that. There are only 2 hard things. Oh yeah, it's the standard joke. There are only 2 hard things in computer science: cache invalidation, naming things, asynchronous callbacks, and off-by-one errors. It's like a super standard joke in IT, I would say. What is the best way to work remotely in security field? I'm not sure I understand the question. I mean, are you asking how to find a job, or are you asking how to set up everything? How to find a job? Well, that's the usual way, right? Just note in your resume or your application that you're looking for a remote job. or look for job offers which has the word like remote in them. And apart from that, it boils down to you actually working. It's good to have a separate room for an office, so you go to an office and you focus only on working there. You don't play computer games and so on in that place, and then you actually do have to you know, be the boss of yourself in that case and be sure to work to fulfill the contract. It's not super easy, but it has its advantages. At the beginning of my career, I used to work remotely to both my first and my second employer, so yeah, it's doable. But I guess you start to it's not great that there are not a lot of user interaction. If you work in the office, especially with super smart people, then it's like, yeah, like let's grab coffee and discuss this problem. That's like super awesome thing that you can do in an office with smart people, which you cannot do working remotely. But just doesn't work like that. Yeah, I don't know. I probably didn't answer the question, but just send me an email if you have more questions. Like, yeah. Any advice for a new CTF team? My usual advice to new CTF teams is read a lot of write-ups. You don't have to fully understand them, but you have to know that something exists and how to approach a problem, and during a CTF where to find that write-up. And this is true, like, for example, you are, I don't know, like starting a new task and it's like some wave file. How do you approach a wave file? If you read like 10 write-ups and there were like wave files in 3 of them, then you can go back to these wave files, to these write-ups and see how to start with the task, and that usually gets you going. So read a lot of write-ups. You don't have to walk through them, you don't have to do the same thing, you don't have to solve a challenge, but do read the write-up. So that's my main advice. Apart from that, just play the CTFs. Yeah, that's about it actually. It's also good if the members want to like solve some wargaming challenges from time to time. That's also quite helpful. This challenge looks easy with IDA, the compiler you used, which is quite pricey for hobbyists. Do you know any free decompilers that would help with challenges like this? Actually, in both challenges, I used the compiler just to save time. You wouldn't have to use it. The assembly there wasn't obfuscated. It was quite easy to read. That being said, I fully agree that it's faster with the compiler. That's why I used it, right? I don't know of any free ones. There are a couple of free ones. Like I think Boomerang was one was called, and I'm pretty sure there was another one. But I didn't look up free decompilers recently, so just Google it. There might be a couple of ones. They usually are lacking, especially that, you know, IDA's the compiler is actually interactive, right? While others aren't. So yeah, I don't have any good recommendations. I actually hope that Binary Ninja, they have a good idea for the compiler for Binary Ninja, and I hope that when that comes in, that will be decently priced for CTF players. So yeah, let's wait for that. Can you make a stream dedicated to solving crypto challenges, explaining the basic attacks, similar to XSS stream a while ago? Anyhow, you are doing a great job. Thank you for sharing. Thank you for the kind words. I'm pretty sure I did an EAS livestream, but that might have been in Polish. I will take a look. Actually, that's not a bad idea. So let me note that as well. Yeah, I'm not great at crypto. Okay, so it would be the basics, and it would be only about a couple of things. I'm decent with AES, I'm decent with RSA. I have no idea about elliptic curves, for example. So yeah, we'll okay, we'll see. Okay, so Foxtrot tells me that the AES one was in Polish. We can do it in English then. That'd be cool. Okay. Przemek, I've read on Microsoft's site that the whole trusted boot once secure boot is enabled and every component verifies the next one has been implemented in Windows 8 and later. Yeah, I'm pretty sure when you're using disk encryption from Microsoft, it is there, because I've seen, like, when pulling out a network card, it actually complained that now I need to enter a recovery code because my hardware changed. So that's kind of fishy. So if it's really me, then yeah. So yeah, that's probably true. I'm not sure if it goes like again, I have no details on the implementation. I'm not sure which parts are actually checked, whether, for example, the firmware is checked in the graphic cards and so on. What do you think about the new Gmail layout? It's so slow, laggy, and doesn't scale well for me. It's a good question. Actually, I switched to the layout as soon as it was available, which actually means before it was public, right? And I didn't feel any difference. For me, the way I used the previous layout and had it configured, it like works the same way, everything looks the same way. So for me, the passing from the old layout to the new layout wasn't actually a big change. And it seems to work fine for me. Actually, I didn't have problems with lag, but you know, your mileage might vary. So yeah, it works for me. Did I see the Microsoft/MS-DOS repository on GitHub? Yes, I did. So it's a cool thing to look at. I did already, so do it. I'm really happy that they shared it. I'm looking forward to looking at source code of DOS version like 6.22 or something. Okay, I think that's all the questions. Oh, Lojax was a malware in UEFI. I didn't look at it, so sorry, I just have no information. So that's it for today. Thank you for being here. Thank you to Foxtrot Charlie for being my moderator today. And I hope there will be a stream in 2 weeks. There won't be in 1 week, I'm sorry about, but there might be one on a different weekday though, so we'll see. And yeah, that's about it. So, oh, there's one more question. So I'll quickly do this question. In one video you explain Spectre Meltdown, but how can we patch those vulns? Is the Linux kernel update enough, or should BIOS also be upgraded? I don't have the details about how exactly it should be patched. I know that so if it boiled down to the microcode updates, then it doesn't matter if it was done on Linux or BIOS side, because both can actually upload a microcode update. Because microcode updates have to be uploaded after each reboot. They are not like, it's not like, what's this called, non-volatile storage, it's a volatile storage. So every reboot you have to upload the microcode updates again, and the kernel can do it for you. So yeah, if there are patches, they were probably in both places. Okay, that's it. See you in 2 weeks. Thank you, Foxtrot Charlie, and that's it. Happy hacking, and see you later. I'm going to leave you with some music. Bye-bye.